as a teacher, I really like to follow this. It's very near and dear to me, right? Maybe 5 to 10 minutes, okay? So first exercise is, I've given a C program to print arithmetic series and its sum until the nth term. Okay? So for that program, I split that into 2 columns here. It's just one program. Groups of 2 or 3 on a piece of paper, analyze the program. Take some n value equal to 5, as it says here, right? What is the output for n equal to 5? Okay. Trace it, and then tell me what is the big O and what is the theta for the program. Okay, that is question number 1. The second one is at the bottom. It's kind of hidden in this thing, so bear with me. I will try to. There. Second one is, I want you to simplify that term that I gave you. Okay, so what is the simplified answer for that term? Okay, these are the 2 questions. 10 minutes starts now. Right? So, even in exact analysis also, remember we ignored the constants and coefficients and things like that. And then we did some samples to see the differences between big O and theta. We did in-class exercises. So you have to apply that knowledge to this program. Okay, while you're doing it, I'll go get myself a cup of tea. And 5 times, right? So, and then it's going to scan the difference value, I think, right? Because you need to know the difference in arithmetic progression, right? So if the difference is 2, then the arithmetic progression will be 1, 3, 5, 7, 9, right? So then you do for I equal to 0, I less than number of terms, that is 5. In this case, I think it is 0 kabatti, terms would be value 4, I plus plus, so you go through that. So you get 1, 3, 5, 7, 9 added. That is equal to, that is arithmetic progression, right? So if you look at it, you get, what is the order for that, since the for loop is 5? N. Correct? Don't agree, that's fine too. Maybe I'm screwing up, right? So which I do, by the way, I do make mistakes. Sometimes on purpose, sometimes genuine mistake too. So it's of the order of n. What is the difference between big O and theta? Theta is if you are able to count the instructions exactly, right? Oftentimes we don't count, we cannot count all the instructions. Since it's a toy sample here, we can actually count the instructions too. Just like how I did pretty much here. If I trace it, I can count, and then you eliminate the constants, because the main thing here seems to be the for loop, and it's going to do it 5 times, so it's going to be order of 5 for that too, or order of n rather, whatever that I value is, right? So both the big O and the theta are one and the same in this case. Okay? Now, second question, simplify 16n cube log 8. I don't know why they put log of 8 there. Don't ask me why. I copy pasted it from somewhere, right? But if you simplify, our logic, we said, we should see what is the fastest growing term. And other terms which do not grow as fast as the fastest, we eliminate. So if you eliminate 100, you can eliminate the n squared term, right? 100n squared. Then you can only deal with n cube, 16n cube log some base 10n squared. That is one full term. You can eliminate, the logs, right? 10n squared log 10n squared, 2 just by together, 2 log 8, 10n out. Correct? So you eliminate coefficients, you eliminate 16, you eliminate 2. And then 10n, you eliminate 10, and then you are left with log of n, and n cube. So if you simplify, that term comes to NQ log N. That is a simplification. Understood? You have to remember your logs and use the N. How N is going. As N tends to infinity, we said that these constants and coefficients do not contribute much to the growth compared to N. Or N whatever N squared, N cubed, whatever that is. Okay? Good. Last week, this is kind of like a summary for you. When you review the slides, everything is explained. It's almost like this particular and theta. We also have another symbol called big omega. Okay. So while the O is meaningful because it tells us, what does it tell us? It tells that our program will never be slower than a specific bound. And that is the upper bound. Worst case. It won't be slower than that. Okay. So if that is good enough, of course we move on, right? Excuse me. The opposite of that, okay, meaning if we can somehow make the program better than the big O, okay, then that complexity is known as the big omega notation, okay. So as the second bullet says, what big omega basically gives you a lower bound. While O gives you an upper bound, big O, the omega gives you a lower bound. Okay. Now it's important to know that lower bound also is still worst case analysis. Okay, don't get me wrong. It's not like most optimum. Okay. These are all part of the worst case analysis because we are eliminating constants, we are eliminating coefficients and all that. Okay. But at least we are saying this is slightly better than the O. O is really worst case. Okay. 1 second. Worst case, upper bound, the omega gives you the lower. Okay. Now, just like as big O has a small O, big omega has a small omega, shown like the W symbol, right? We call it small omega. Because we talked about tight bound. When you do theta, you get that's exact analysis because you're counting the instructions and so on. So you can get a tight bound. Same thing, when you can get a tight bound to omega, you call it that distinguishes between the tight bound of omega versus not tight bound of omega. Okay, so that is the theory. Now, all theory is great. What are the three most important symbols? Big O, theta, and big omega. And then you have the small symbols too. Small O and small omega. Now the reality in life is, the real reality is, you are a programmer in the industry, you have a deadline to meet, you write some algorithm, make it work to keep the manager happy. Because the manager is clueless, right? About programming, most of them. But if you have a little bit of what I call it a self-pride, you do some analysis, right? Most of the time, the analysis that we do is just worst case analysis called big O analysis. Okay. So, for the sake of completeness, I covered all three of the notation. However, only the most going forward, when I say compute, I usually ask you to figure out the complexity at the O level, big O level. Okay. And I gave you some other pointers when you can say big O versus small O, right? If it is not a tight bound, if big O is not a tight bound, then you make the symbol small O. In the exercise also, we did one of those samples. Okay. Go to the next slide, Andy. Thanks. Write down for this exercise. We'll not do it right now because I want to continue with the lecture. There's an exercise saying where we have these theta complexities. Write down a tight and a non-tight O bound. Okay? And a tight and non-tight omega bound of your choice. Okay? provided they exist. It's actually not providing, provided. I made a typo there. It's provided they exist. If you go to the next slide, you'll actually see the solution. So I had to do not a straight copy paste. I had to use my snip tool. Sorry if the text looks a little bit weird. If you maximize the screen, and you can actually see it on the screen. Okay? So that is the solution. And during some break time, I want you to review that exercise and the solution. Okay? And then if you have any questions after looking at it, go to the next slide. Okay. So now we are going to have some quick overview of the logs, right? Because a lot of our algorithms, as we keep moving forward, you will get logarithmic analysis. Quick review of the log. I assume that you know this stuff, how to do the logs. Log A B equal to log A plus log B, and there's a proof there. Similarly, log A over B is log A minus log B, and log A raised to B is B log A. And when we talk about logs as computer scientists, as you know, we talk about logs to a base 2. Okay? If you have forgotten logarithms, you may want to review that on your own. Okay? Go to the next slide, Andy. Okay. So a couple of more notations here for the definition for those of you who have missed. When we talk about upper bound, we talk about big O. Okay? If you are mathematically oriented, you can see how the mathematical equation is given there below. Don't worry about that too much right now. All you have to remember is upper bound is big O, lower bound is omega, and exact is theta. That's why the exact one is called tight bound. Okay? Go ahead, next slide. Okay. Now, when you do your algorithmic analysis, these are all the types of things that we'll get in increasing worst case. Increasing worst case sounds like an oxymoron to me. Order of 1 is the best. When you do complexity analysis, you can't go below 1. 1 is the lowest unit, okay? Next one is O log n. That is. Thank you. Now, Chakravarti is using all the tools of WebEx. I'm glad. Now you see why the whiteboard of, or even WebEx tools, they are not that great compared to my app. The next better log tarvata linear. N log n is the other one. Afterwards quadratic, cubic, and so on, polynomial. So the goal, of course, is to most of the algorithms, if you can achieve log or n log n, they are good. Okay. Log is always lower, remember that. Okay. So next slide, please. If you really want to tie it to your mathematics concept, right, we take this asymptotic notation. You can see for big O it is less than or equal to, and it's like worst case, right? And then you have the omega, which is greater than or equal to lower bound, right? And then theta, of course, is exact. And for the small notations of O and omega, it is, you remove that equal to sign, it becomes truly less than and greater than. Again, I don't waste too much of your brain cycles trying to understand that it's there. You don't need to memorize that, but as a formality, I put that slide in there. Go ahead and do. Now, we kind of talked about this last class, right? Running time will depend on the actual data input, not just the length of the input. Remember when I took an example of an array where you had an array which was already in 4, 3, 2, 1 order versus an array which was in 1, 2, 3, 4 order, depending on the actual data input, depending on how the values are, it executes more number of instructions or less number of instructions. Okay. So typically when we do the analysis, we do worst case, best case, right? Average case, and amortize. So amortize is nothing but basically an average time over many operations. Again, we don't really get into amortized complexity analysis in this class. I'm mentioning that term here because it's listed in Unit 1 table of contents. And then there's another one, average case is interesting. That's where you get into this probabilistic distribution of input. Oftentimes, you use probability all over the place, right? If you're doing surveys, voting, polling, all of those things are probability driven and random. So even if you take quick sort, we didn't see quick sort yet. Quick sort is really a randomized algorithm in a way because you can choose a pivot, something called a pivot, a reference point. You can choose that randomly. Now once you choose those things randomly, depending on the probability of how the input distribution would be, distribution can be normal distribution or it could be something else, right? But people can still come up with the complexity analysis. That is where we get into this average case and amortized cases. Next slide. Again, still a little bit of theory. Okay. So these are all the types of terms that we use when we talk about the complexity analysis. On the one hand, you can hear computer scientists talking about upper bound, lower bound, and type. So there's a big O, omega, and theta. Okay. You can also talk in terms of, hey, what is the worst case? The moment you say that's if you're talking to your manager, right, about this algorithm, the guy won't have any clue about omega, theta, and all that. That's truly Greek. There's the Greek thing, right? But they would say, okay, what is the worst case for your algorithm? How much time will it take? Then you know, oh, he's referring to the best big, right? And so on. See the simplification that I was talking to you about for the 16 and cube? Here is the answer there. And how we arrived at the answer is given in the steps, which you can review at leisure at a break. Next slide. So we are doing some in-class exercise today actually. We can go to the next slide. So you're reviewing that. I'm not reviewing it. They can. Okay. Now the fun begins. Okay. So we saw some complexity. Big O, again, typically what happens when we do big O analysis, we look at the for loops. Okay? So, like for example, you had the array. Remember we did an array example in the first class or second class. When you have an array of elements and you're searching for an element, I said what is the worst case there? Big O analysis. So how do you search for an element in an array? You write a for loop, right? Say for I equal to 1 to n, right? And then you store the search key in some variable s. Then say if s equal to a of I, then you found the search key, right? Now, if you are unlucky, you will have to traverse all the elements of the array. Maybe only the last element would be. That means the worst cases you have to cover n elements of an array. It means you have to run the for loop n times, correct? So big O is basically that. You say, hey, here is one for loop. The worst case you have to run it n times. So the big O says it's order of n. That algorithm is the order of n algorithm. Okay? Typically from for loop. Okay? Now, if you have like a two-dimensional table, some kind of a matrix multiplication, you know from your high school math, how many for loops you have in a matrix multiplication? If I'm not mistaken, there are 3 for loops, right? Okay, so when you have 3 for loops, each for loop takes n times, then the big O for the matrix multiplication order of n cube. Because you have for every one element of the array, is basically n times n times n. So it comes to n cube. Okay. Now here is an interesting example as opposed to those for loops. There are no for loops here. It's a recursion. You all know what recursion, right? So when you have a recursion, you have a base case. Base case is if n equal to 1, you return 1. If n is not equal to 1, then you say return n star, in this case factor n minus 1. So in recursion, you have a base case, and all other cases, you keep calling the same function. Okay? Now, 5. 5 seems to be a magic number to it. Let's take n equal to 5. What happens? Trace it. You know how to trace stuff, right? You say, okay, factor 5, then n equal to 1. No, it's not. Return 1. So trace one line, second line, next number, like that. Trace it. Initially, you start with factor 5, right? Then you go there, then maybe next level you'll say factorial 4 maybe, like that. Is that also a tight bound? Is that a theta n also? The tight bound. In the chat, what to say here? What logarithm you are finding each case? Okay. Denote what logarithm you are finding in each case. Lovely, Andy. You are doing a phenomenal job. I appreciate that. So basically logarithm take the exponent column together. I assume you understand that, right? I also know half the students would have forgotten logarithms. But that's why you team up with somebody and then make it happen. Pretty straightforward. We'll do it as a group exercise. It's not like whoever has the answer, you can put it in the chat and then we'll move on. And when you put it in the chat, put it for everyone. 6, 2 raised to 6. You got it. Pragati, go for it. You got it. What about the next one? The 2 raised to over x. I don't know what the terminology is. I got it. I think it's simplified to 2 raised to 2x, right? Multiply those to 2x, 2 raised to 2x. Think for a second. 2 raised to 2x, so 2x, right? 4 it is 0. See? What about 5? Is not a faculty member system. See, there is nothing that I do without a reason. Okay? Most of them. Sometimes I do it for a reason. Okay? Great. So, the reason I wanted you to get what in logarithms is, we will have logarithmic complexity in our analysis stuff. An example of that is binary. Okay? So here is a binary search. What is a binary search? First and foremost, I want to make you review this code, okay? So, but one of the things that remember is, it is a sorted array. In this case, we're not talking about trees and all that yet, okay? We are just still in the realm of arrays here, okay? So we have a sorted array, that is A, okay? And then you have the size of the array, that is n, okay? And then the value that you're searching for, okay? So here is some kind of a pseudocode or some kind of Python code. You are using, if you look at line 8, so after the base case, you are calling the binary search again. Right? You see that? Okay. I think on the next slide I asked you the questions, I think, for this program. Oksari miru cheat chesi. Yeah, there you go. So, ఒక్క నిమిషాలు చూద్దాం ఇక్కడ ఏం రాసిందని. Okay, got it. you to study the program, that's where you will do it again, is what we are saying is the zeroth iteration. We call it iteration here. I think we call it iteration in India too, right? You have n elements in an array, right? After the first iteration, you have n by 2, and so on. So the question that you have to answer is, how many elements will the array have in the ith iteration? Okay. So the way you would solve the problem is, you go back to the previous slide now only. So study this now and tell me, you can draw a piece of paper. What I want faculty members to do with the students is, on a piece of paper, let them draw an array, a single dimensional array, sorted element. Okay, let's call it like a 5-element array or 6-element array. Okay, let them trace this program with that. Somebody already put that. N over 2 raised to I. That is the answer, okay. But, okay, since, okay, C Prakash, they are also answering that. That's good. Because it's easy to figure that out, right? If you go to the next slide. Yeah, everyone got that. N over 2 raised to I, right? If you see, for example, third iteration, right? Third iteration is, if you see 8 is 2 raised to 3. If you look at the second iteration, n over 4, second iteration is 2 raised to 2. So ith iteration is n over 2 raised to I. Okay, got it? That's how you arrive at that formula. Okay, now go to the next slide. Of course, last iteration would be 1, right? Because by the time you come to that, excuse me. Now go back to the previous slide. Yeah. So when you have 1, that last iteration, and then if you look at the equation that you get out of that is, ultimately, you want to get to 1 when you have n over 2 raised to I. So what is I equal to? Is what I'm asking. So how many iterations you would do? You come to 1 element. The moment you come to 1 element means you found your value or you didn't find your value, right? What is I equal to? I is not equal to 1. So I equal to log of n base 2. Based on the other formula that we did, right? The small exercise that we did. So all of a sudden, what you have for the binary search, go back to the binary search algorithm. Go back a couple of slides. Yeah. So that algorithm that you see, binary search, forward. You went a lot of slides back, okay. Yeah, no. You went back as opposed to forward, the binary search algorithm. You have the, when you have a binary search algorithm here, all of a sudden what you're doing is that every step you're dividing it by 2, half, and the analysis showed there, basically results in log of n, right? So this particular algorithm, you can find a value depending on what the size of n is in log of n time. Now imagine you have, of course it is sorted, okay? Imagine if you do not have a sort, it's unsorted array, then you have to search. Unsorted array, not binary, normal search, meaning you're going from A0 to AN. Potentially you're searching all the elements of an array. We did that, right? In the first example, we did that. In the very first day, I think we did that. So that will be order of n algorithm, linear search, right? Linear search is basically order of n algorithm. But by sorting the array, okay, if you have a sorted array, then it comes down to log of n. Log of n is a significantly smaller number compared to n, right? That is what this is showing for you. Okay? So, this introduction and these examples that I showed you in this slide deck should show you, hey, this is really fun to come up with algorithms and so programs, right? Programs are manifestations of algorithms, right? Where we can write some cool programs, right? I don't think you would have thought along those lines when you learned your C programming unless the professor who taught C programming was passionate about complexity. I don't think the focus was on that, right, for that class. But now, once you take this class, here onwards, whenever you're writing, okay, and then doing a quick analysis. See, ultimately, all said and done, you don't write one big monolithic million lines of code, okay? You apply object-oriented principles, you have classes and things like that. Each class would have a method. A method should be no more than a page or two of code. And it's easy to analyze a method, right? 2 pages of code, 3 pages of code, it's very easy to analyze from a complexity analysis viewpoint. Okay, let me pause here. Questions, comments. Very important introduction now, right? We define what algorithms the code are. Right? And then I gave you definitions of or the importance of performance. Right? We talked about time complexity and space. We said about the storage space. And we gave a definition for asymptotic notation. Asymptotic is what we said, you eliminate all the constant factors and the coefficients. The process of filtering out those things is what is asymptotic analysis. Okay? Once we did that, we introduced the big O omega notation and the theta and their counterparts. And I briefly told you what probabilistic analysis and amortized analysis is. To really get into more details of those two things requires a little bit more deeper knowledge than what you have right now. So if time permits, later part of the classes, I will give you more examples of probabilistic analysis and amortized analysis. Okay. This document will be currently one of the things, classic thing, the binary search that we talked about. Like a divide and conquer algorithm, right? You're dividing your search space. Every iteration, you're dividing it into 2. Okay? And then 3 most important algorithms in the divide and conquer approach type of algorithms is the binary search and the quick sort. And then there's something called a merge sort. Okay? So that would be the focus for next 2 weeks. Okay, now go back to my slide deck, and as always we have the last 20-25 minutes of the class to do some good exercises, right? At least 20 minutes. Today you got a little bit more time. So faculty members, please facilitate this one. Don't let them leave the classroom, lock the doors. I'm just joking. Hopefully you don't have to lock, they are motivated, right? Groups of 2 or 3. Okay, so I gave you the binary search algorithm, the sorted array. Okay, pretend you're writing on a piece of paper. No laptop, no cell phone, and all that. I want you to literally write this algorithm, translate the algorithm to C programming language. Okay, that's first exercise. Okay. So after you take down that one line in your thing, Chakravarti Garu would put the binary search algorithm on the screen, okay? The one that I gave you. How do you translate that into a C programming language? Declare variable, integer I, j, k, whatever you want to declare. You know how to declare an array. Okay? So when you do that, excuse me, how would you solve that? That's number one. Once you do that, I want you to figure out in an exact way that it is indeed a log algorithm, right? You already know it's a log algorithm, but after you write also you can figure it out. Then second thing is write a quick sort program to sort an array of elements. Because remember, binary search works if the array is sorted. So how would you sort an array of elements? Somebody put some exercise, like bubble sort, selection sort and all that in the community. What I want you to do is do a quick sort algorithm. Now, I didn't teach you what quick sort algorithm is, but you're smart enough outside of the classroom to figure what a quick sort is. If you Google it up, you'll get it, right? The trick is to understand what you see and then write a program. You can copy also a program from internet. If I were you, I'll try to write the program first. Okay? And after you write the quick sort algorithm, I want you to tell me what the complexity of the quick sort algorithm too. Remember, I told you how to do the big O, right? So we're talking about big O of the quick sort algorithm. So remaining time, you do this in class as much as possible. I think you should be able to knock off bullet number 1. A rough draft of 3 programming, so 2 or 3. Whatever you write on a piece of paper, go implement it in your lab outside of the class. You have a computer lab, if I'm not mistaken. Go see if your program works. If not, make the necessary changes and make it work. Okay, questions, comments? Writing well.